All right, I'm back. Sorry about that. Just had to hop on a quick call. All right. I did want to pull up something in my browser here before I forget. Actually, no, I'm just going to jump over here to Learn Log. There was a thing that my buddy sent me this morning that I wanted to read, which is MPAC faster, more flexible integer compression. Which it's message pack. I think it's this thing here, but I have Reddit blocked, so I can't view that. But if I go over here, I say, hey, it's on blog CF8 GG. Maybe that'll help it. Not really good search optimization on their end. blog.cf8.gg. If I can type right. There we go. So it's Vim readme. It's gonna be blogs. And we'll bust open this, throw that in there. Oops, throw that in there. Delete that. Here we'll just say copy pasta. Cool. I will get around to reading that at some point. Not right now, but I wanted to record it into my README. If I can, please right click all. Thank you. Kill this thing. We can kill that now. And yeah, let's go ahead and finish watching this lecture.
And so just looking at the low order 4 bits, our 0, 1, 1, 0 is 6. And indeed, that's -3 times -2 is 6. So the point being, and I'm waving my hands here because I don't want to go through all the details, but 2's complement multiplication also gives you, if you can do it using the exact same rules and as you do for unsigned multiplication, the exact same hardware. I should mention that there are instructions in the computer in ways that you can get the upper word of a multiplication too. And those, the bit patterns are different depending on whether it's treated as a 2's complement number versus unsigned. So there's typically different instructions for doing that computation. But 99% of the time or more, you just are looking at this lower part of the product, and that's the same whether it's a 2's complement or an unsigned. And it handles negative numbers positive, but it has these overflow characteristics. So as I was talking about, there's a trick we can do for multiplying by a power of 2, which is just to shift the number to the left. And you'll often see that when you have in your code, I want to multiply some number by 4, you'll write in your C code. If you look at the assembly code, you'll see that what the compiler generated is just says, oh, just shift it left by 2. So in general, and you can see why this is true, by the way, if you think of the number as the sum of the bits where x of y is the ith bit and x is the number it represents. If I want to, if I shift everything left by 2, what I'm effectively doing is increasing their weight by that number of positions. So let's just shift by 1. If I shift everything to the left by 1, which we write like this in C, 2 less symbols. It's like taking that sum, but now weighting the bits by 2 to the I plus 1, by 1 more. And of course, that's equal to twice what the original sum was. And so we double the number. And that works also even if you shift things so that you lose some bits, right? They shift off to the left. All you're doing is the way multiplication works anyhow of truncating to a W-bit product. So you'll see this, as I mentioned, quite often in compiled code and machine level code that they're doing shifts where you might expect them to be doing multiplications. And the reason for that as an optimization is historically the multiplication instruction took a lot longer than a shift instruction. Say 1 clock cycle to do a shift And it used to be like 11, 12, 30 clock cycles to do a multiplication. Nowadays, like on the computers we use, the Shark machines, it only takes 3 clock cycles to do multiplication because they added a lot of hardware to do that. But 3 clock cycles is still more time than 1. And so when you can get away with a shift, it's generally a better idea. And the compiler has its own kind of judgment calls on when is it more efficient to substitute one operation for another. Did I lose ground here? OK. So the idea then, if we want to multiply something by 2 to the k, we just shift it left by k bits. It turns out that the same almost works for dividing by 2 as well, that if you want to divide something by a power of 2, you can shift it right by in the same general idea. The only thing that becomes a little bit quirky is, well, what if the number you have is not actually divisible by that power of 2? So for example, if we had the number 0, 1, I'm going to use this. Yeah, so that's 6. So if we shift it right by 1, we'll get 0, 0, 1, 0, 1, 1, thank you, which is 3. And that's 6 divided by 2 is 3. If we shift that again, we'll get 1. But of course, you know that 3 halves, or 1.5, the rule on integer division is you round it down, round it towards 0. And so that goes to 1. So this is what the unsigned case works fine. The signed case, which I don't have a slide for, is a little bit less pretty. Well, first of all, you notice if it's a positive number, the shifting right is going to be the right thing, just as it is for unsigned. But let's take a number that is negative. So this is minus 6. Right? Now, here's where, remember I told you in the previous lecture, there's 2 ways to do shifting. There's logical shifting, where you fill in with zeros, and arithmetic shifting, where you fill in with 1s. And guess where arithmetic shifting comes in? This is it. When you want to preserve the sign of a number while you're dividing it by powers of 2, you want arithmetic shifts. So if we shift this by 1, we'll keep that sign bit and then copy the other ones over. Right? So we just preserve this bit here and copied the other ones over. And this is minus 3. And so that's good. But now if we shift again arithmetically, we'll get what?
Minus 2.
Minus 2. I can see it. You guys need to know how to negate numbers, right? You don't know that? So I'll show you in a second. So here's a little bit problematic that we shifted. We want to divide by 2, but the rule should be the same, that you should round toward 0. And what this is doing is it's rounding toward minus infinity. It's rounding toward a more negative number than the true thing. Yeah. And so there's a cute little trick that says before you divide by a power of 2, before you do the shift, you should add a bias. Which in this case would just be 1. And I'll tell you where that comes from. And so if we add those numbers together, we'll get 1, 1, 1, 0. Right? And now when we do the shift on that, we'll get 1, 1, 1, 1. And that's minus 1. So there's a trick. And you'll see the compiler doing this, where you have in your code divide by 16. And it will add a bias. And then it will do a right shift instead of calling division. And by the way, division really, really is slow, even on a modern computer like what you have, the Shark machines. It takes 30 plus clock cycles. So anytime the compiler can figure out a trick that does it with shifting and tweaking things around, it will. So I realize I should tell you there's a couple ways you can negate a number that are handy to know if you ever have to do it in your head or on paper. And the standard way is what's called complement and increment. Yeah. So this is how do I go from x to minus x. So if I have a number and I want to negate it, whether it's currently a negative number or it's a positive number, the same trick works. What I'll do is complement it, meaning I'll flip all of the bits. And then I'll add 1 to that. And do the regular sum. And so this is 6. This is minus 6. So if you ever have to do it by hand, that's the way to do it, complement and increment. And it goes the other way. You'll see if I complement this, and I increment it, I'll get back to my previous number. So that's a trick that is pretty much only useful when you do things on the blackboard or when you have to solve a problem in data lab. Anyways, this idea of doing using a shifting to the right to do power of 2 division is actually, that's the whole justification for arithmetic shifting in the first place. Which, by the way, in C, there's no fixed requirement for how shifting works in C for signed numbers. For unsigned, it has to be a logical shift. Signed numbers, the C standard says there's no fixed definition. The reality is on our machines, most machines, anyway, in C, using a shifting to the right to do power of 2 division is actually, that's the whole justification for arithmetic shifting in the first place. Which, by the way, in C, there's no fixed requirement for how shifting works in C for signed numbers. For unsigned, it has to be a logical shift. Signed numbers, the C standard says there's no fixed definition. The reality is on our machines, most machines, just about every machine out there, when it's a 2's complement number, when it's a negative, when it's a signed number, it's 2's complement. And when you do a shift, it will be an arithmetic shift. So getting back to then summarizing this integer arithmetic, you see that, first of all, whether it's signed or unsigned, the addition or multiplication operations are the same, whether it's a unsigned number or 2's complement. And it works. The negative stuff works out as long as you don't have an overflow. And you can end up with an overflow, only one type of overflow for unsigned and 2 types for signed numbers. But it's not like they just overflow and generate random numbers. There's some a pattern to what they are and how they can be interpreted. So I talked about this a little bit last time and gave this example similar to this, but let me go. There's multiple back to them. So getting back to then summarizing this integer arithmetic, you see that, first of all, whether it's signed or unsigned, the addition or multiplication operations are the same, whether it's a unsigned number or 2's complement. And it works. The negative stuff works out as long as you don't have an overflow. And you can end up with an overflow, only one type of overflow for unsigned and 2 types for signed numbers. But it's not like they just overflow and generate random numbers. There's some a pattern to what they are and how they can be interpreted. So I talked about this a little bit last time and gave this example similar to this, but let me go over it a little bit more. One thing you might think of, wow, if this unsigned and signed stuff gets so murky, and we saw some funny examples last time, maybe we should just banish unsigned numbers from the universe and only allow 2's complement. And that's exactly the rule that was adopted, for example, in Java. They said, oh, this is too weird. Let's just say every number is 2's complement. The only trick they did was they put in a triple right shift. Means logical shift. This is Java. This is not C. Whereas the double is arithmetic. So because they realize there's a lot of cute little times when you want to play tricks with things, and you need that logical right shift. So that's actually one approach. Or other more modern languages in C are saying it's OK to have signed and unsigned, but we don't want them sort of mysteriously being cast back and forth in ways that the programmer might not recognize. And so you have to explicitly do a cast rather than implicitly. And I think that's the better approach. But C, as I mentioned, might not recognize. C are saying it's OK to have signed and unsigned logical right shift. So that's actually one approach. Or other more modern languages in C are saying it's OK to have signed and unsigned, but we don't want them sort of mysteriously being cast back and forth in ways that the programmer might not recognize. And so you have to explicitly do a cast rather than implicitly. And I think that's the better approach. But C, as I mentioned, does this implicit casting. And so as we saw for last time, what happens with this program when you run it? To count down through an array?
Doesn't run.
Do you remember?
It runs forever. Let's look. So we got delta I is equal to count. Count, say, is like 100. So you're going to have like 100 minus delta, which would be 4. Is greater than or equal to 0. Then you're going to decrement delta. sorry, you're decrement I by delta. So I is going down. When I goes negative, then it goes really high value. So basically, it's going to loop forever. It's an infinite loop.
If it's unsigned, what will happen with this test? It always succeeds. So the thing will be in an infinite loop. Actually, what will happen is it will try to access. I will go down to 0, and then it will wrap around to become the largest possible unsigned number, which is probably way out of bounds, and it will give a memory error. But it won't do what's supposed to be. And as I mentioned before, these things, there's a lot of sneaky ways this problem can show up in ways you might never think of. So for example, the operator size of is defined to say how big a particular data type is. It's a very useful operator, but its return value is what's called a size underscore t, which is defined to be a long unsigned number. And so if we just throw in a constant like this, then this subtraction, we have a sign, I is now int, but size of is unsigned. And so it will cast that to be unsigned implicitly. And when you compare it to 0, you'll have the same problem as before. So just to show you that these things can sneak in very tricky ways. So one way to do that then is just don't use unsigned. And make sure if this is a possible unsigned number, you cast it to signed. You make sure that this is recognized as signed. But there's another way that actually, at least there's a fellow over at the Software Engineering Institute named Robert Secord, who has written the books that are sort of considered the gold standard for how to write secure code.
Interesting. Secure coding in C and C++. I haven't heard of this one. Let's add that to our list. Vim, oh sorry, I need to jump over to learn log, Vim readme, books, in the queue, we'll put it somewhere down the bottom, above the cert thing, yeah, because that's also security related. This will be on my security. Let's see here. Second edition. Oh, good lord. Good lord, that's a URL. Let's just grab this part. There we go. And we'll grab the name. When was this published? Second edition. 2013. Okay. It's a little dated.
Computer emergency response team, which is out there tracking down bad things going code. He works for this organization called the Computer Emergency Response Team, which is out there tracking down bad things going on in computer security. And one of the things he and others have done is to try and come up with standards so that people who write programs will avoid some of the pitfalls that make their programs vulnerable to.
Okay, proper way to use unsigned as loop index. Yeah, I mean, that's the way I've always done it. Say I is less than the loop index versus less than or greater than or equal to. And you do your increment on I. In this case, decrement. C standard guarantees that unsigned addition will behave like modular arithmetic. Even better is to explicitly type your index to be a size t, so you're doing unsigned arithmetic in comparisons.
Attack. And so his recommended technique is, when I first saw this, it was so counterintuitive to me, it hardly made sense, right? So you start, and again, this is all unsigned arithmetic. So I'm starting to count down, and my test is when I is less than count. So here's the thing. I started off smaller than count, and it's only being decremented. So when would this test ever fail? When it overflows, when it wraps around. Right? When I goes from 0 and counts down to what would now be u max, this test will fail, which is exactly when you want it to stop. And his observation is, in C, with signed numbers, there's no guarantee on what happens with overflowing. As I said, most people just assume it's going to be 2's complement. But if you really want to be careful, you shouldn't assume anything outside of the C standard. And if you're trying to write secure code, it's probably a good idea to be cautious, be conservative. On the other hand, the C standard guarantees that unsigned arithmetic will be modular arithmetic. So it guarantees that if you subtract 1 from 0, you'll get the largest number that could be represented. So it will be OK. And in fact, he recommends instead of using unsigned, which is on our machines just a 32-bit value, that you call it a size t, which is a 64-bit value, and write your code the way that I showed you. So I've actually started doing this. And once you kind of get used to it, it's an OK way to write code. But it's very strange looking initially. One thing I'll point out is what would happen if count were a signed number, an int, and it was less than 0? What would happen here? So I less than count, what would happen? Right. And so it would become a very large positive number, and this test would almost certainly succeed. So you have the same. This code doesn't avoid the pitfall. It just shifts it to saying, you better make sure you don't test for this case beforehand before you get into it. So I think part of it is the observation that, man, if you want to be careful and write code that is guaranteed correct no matter what implementation goes on, as long as it's within the C standard, it's pretty tricky business. A question up there?
So if you count something that mixes an unsigned with an unsigned, the implicit path is always unsigned?
Yes, which is unfortunate. Right? So yes, that's exactly the rule, that it's implicitly, silently, the C compiler doesn't give any warnings. You'll never know. You cast it to unsigned. And as these examples show, when you stare at that code and you think about it, it's really easy to have bugs that you can look at it 1,000 times and not realize that it's a bug. It's a very, and there's examples in the book of security flaws in sort of very important library software due to this problem exactly. So part of the reason we teach in the course is just so you appreciate that this is a quirk in C that, again, 99% of the time you'll never even, it won't bother you at all, but there will be some oddball cases that you can get in trouble with. So the other place that you'll find unsigned representation useful is, first of all, when you're doing modular arithmetic, which is, for example, the way most encryption algorithms work, or when you're using the bits not to represent numbers, but to represent sets, the way I described it before, then you don't want to, it's easiest to just think of that as unsigned numbers. OK, so the final thing to talk about today is some of the low-level representations of numbers within memory. And the main point is when you are running a program on a computer, from the programming perspective, even as an assembly-level programmer, not just as a C programmer, in your mind, the memory is just this big array of bytes that's numbered from 0 up to some maximum number. So for example, in the machines we're using, the 64-bit machines, an address is represented in 64 bits. But in fact, the maximum address you're allowed to use in current machines is 47 bits. And 2 to the 47th is still a pretty big number. So that's more memory than anyone's able to buy right now anyhow. And so that's a reasonable restriction. But the point is that logically, your program thinks that it has an array of that many bytes. Let's try and figure out how big 2 to the 47th is. Anyone know it off the top of their head? So there's a trick if you want to get an approximate idea, which is to say that 2 to the 10th, which is 1024, is approximately equal to 10 to the 3rd. You say, oh, well, that's really helpful. What it means is that 10 bits worth of number is about the same as 3 decimal digits, right? So for example, 2 to the 20th is around 10 to the 6th. 2 to the 30th is around 10 to the 9th. 2 to the 40th is around 10 to the 12th. And so that would tell you that 2 to the 47th is around 128 times 10 to the 12th, which is 128 terabytes, right? Tera, 10 to the 12th. So if you just want to say, get a quick figure for, and of course these are approximations, but if you just want to get a quick handle on how big a number, what range of values can I represent with so many bits of it, this is a really easy trick to do that. So the point is, 128 terabytes.
That's interesting. If I bust open a terminal here, I just want to run a quick experiment. If a cat out proc self maps, and we look at where the stack is located at, it's at this address. So it's going from a low range to a high range, I believe. Just copy both of these, and we're going to launch Python, and we're going to paste them in here. So 0x, this first one, and we'll just delete this. And then I want the binary representation of that. So I'm going to say bin of that. And then do the same thing for this. Bin of that. So these, all these bits, all the way up to here. So you got B7 and D8. So clearly this is the higher value over here on the right hand side. They both have the same bit length. If we look at the length, it should be length minus 2. So it's 47 bits, like he's saying. And then if we say 2 to the power of 47 is equal to that. And then if we divide by 1024 once, I'll just say twice, 3 times. So that would be kilo, mega, giga, terabytes, 128 terabytes. Yep.
It's a lot.
Just need to send a message to someone about this. Is that value conserved? 7 FFD4? No, it's not conserved. That's interesting that this comes out to consistently be okay. Very interesting.
A couple of disk drives will do that for you, but you couldn't buy enough DRAM on a normal budget to get that kind of memory. So that's the current range of values. But logically, when you run a program, it thinks that it has that possible range. Now, it doesn't really. And in fact, what happens is that the operating system only allows certain regions within that memory to be referenced. And other regions, if you try to access them, it will signal an error, what they call a segmentation fault. But logically, at least, it's as if you have this big array of bytes. Now, in reality, and we'll go into this when we talk about how the memory system works in virtual memory, there's this very complex combination of hardware and software that gives the program this image of a very large, what you call flat space, just a big array of bytes, when in reality, it's shuffling between different regions of your memory and even between your memory and your disk drive on your computer to make it implement this particular idea that you have this big array of bytes. And that's all handled, as I said, by the operating system, by the computer hardware, programs, and virtual memory. Logically, had normal bytes, right? But if you just want to get a quick handle on how big a number, what range of values can I represent with so many bits of it, this is a really easy trick to do that. So the point is, 128 terabytes is a lot. You can buy disk drives. A couple of disk drives will do that for you, but you couldn't buy enough DRAM on a normal budget to get that kind of memory. So that's the current range of values. But logically, when you run a program, it thinks that it has that possible range. Now, it doesn't really. And in fact, what happens is that the operating system only allows certain regions within that memory to be referenced. And other regions, if you try to access them, it will signal an error, what they call a segmentation fault. But logically, at least, it's as if you have this big array of bytes. Now, in reality, and we'll go into this when we talk about how the memory system works in virtual memory, there's this very complex combination of hardware and software that gives the program this image of a very large, what you call flat space, just a big array of bytes, when in reality, it's shuffling between different regions of your memory and even between your memory and your disk drive on your computer to make it implement this particular idea that you have this big array of bytes. And that's all handled, as I said, by the operating system, by the computer hardware, and it's largely invisible even to the machine-level programmer, even people writing assembly code. You'll often hear the term word size, and it can get very confusing nowadays because there's no really fixed idea of what a word size is. But roughly speaking, the word size should be whatever the largest number is or the range that sort of signifies how big a pointer is in this language. Or hardware-wise, the largest sort of chunk of hardware for which there's standard support for storing it for arithmetic operations and so forth. So when we say it's a 64-bit machine, what we mean is that it regular and routinely manipulates 64-bit values on arithmetic operations. And also it has pointers, or the values of addresses are 64 bits. Even if, for right now, only 47 of those bits are usable, it's still considered a 64-bit machine. One thing that's strange is in one of the features of machines such as we have is that if I compile a program using a GCC as a standard compiler, I can specify either I want it to be 64-bit code or 32-bit code as a flag. And it will actually generate two different kinds of object code as a result. And we'll talk about these later. But for right now, the point is the hardware itself doesn't necessarily define what the word size is. It's a combination of the hardware and the compiler that determines what is the word size being used in this particular program. And that code can be run on, the point is a 64-bit machine such as we have, and most machines are nowadays, can in sort of a backward compatibility style also execute 32-bit code. And as we also saw, one of the other features is even though it's a 64-bit word size, the data type int, without any other qualifiers to it, is just 32 bits. So there's sort of this mixture of how big things are. So when people just say word or word size, unless they give a precise definition, that's not a very meaningful term. And we'll sort of throw it around when we mean sort of a generic chunk of bits without trying to assume that it has a particular number of bits to it.
Yes, so slides here.
When we mean sort of, people just say word.
Let's see, address, specific byte locations, 32-bit words, 64-bit words, bytes address, okay.
Yes, so one of the things is if we ever get to 64-bit words, it will be 16 petabytes, 18 petabytes, depending on how you define. When those numbers get big, the error due to this approximation gets more significant. But something times 10 to the 15th bytes. But right now, we can only get to 128 times 10 to the 12th. So anyways, the idea that the memory itself is a series of bytes, but we can group those into blocks of words of different word sizes. And the way we do that is usually by assuming that the address of the word is the lowest valued address in it. And we also will generally try to align these so that, for example, a 32-bit word would be aligned so its first byte, its lowest byte, has all zeros in the first 5-bit positions, right? No, 32, 4. I'm sorry, the lowest 2 bytes. Right. So as this example shows, their address is 0, 4, 8, and 12. They should have really written this in hex and said it's C. I guess these are all in decimal anyhow. So yeah, these are decimal numbers. So 0, 4, 8, 12. So you see these are on multiples of 4-bit boundaries. And similarly, the 64-bit words are on multiples of 8. And those are known as aligned words. And we'll see that the compiler works pretty hard to keep things aligned because the hardware runs more efficiently that way. But the main point is that we can just take as many bytes as we want and collect them together and call it a word for whatever word size we need. And I think we saw a variant of this table before, but this is the machines we'll be working on. That the standard int is still only 32 bits. But if we qualify something as being long, then it will be 64 bits, and we'll tend to do that. There's 2 different floating point representations that we'll talk about. And then the main feature of a 64-bit machine is it has an 8-byte or 64-bit pointer as compared to 32. Now, there's one other kind of detail that says, OK, so if a word has multiple bytes in it, what order should those bytes be? Should it be the and there's 2 basic ways this could go. One is that you put the bytes in what's known as Little Endian order, meaning that the first byte in the word is the least significant byte, and then the next, and then the next, and the final byte in the word is the most significant. Or you can flip that around. And those are called Little Endian and Big Endian is the sort of terms for that, which comes from a English book called Gulliver's Travels, which didn't anticipate computers at all. But it's an interesting story of how that comes about. So out there in the world, you'll find both types of machines, Big Endian and Little Endian machines. It turns out that increasingly it's getting hard to find Big Endian machines. So Little Endian, all of x86 is Little Endian. And it turns out ARM processors, like what you have in almost every cell phone here, is an ARM processor. And the hardware in those can actually be configured to run either way, Big Endian or Little Endian. But when you're running it on any of the standard operating systems that run on ARM processors, then it's running Little Endian. So there used to be a brand called Sun Microsystems, and they were fairly common on campus. And then back at the Macintosh, before they were x86 processors, they ran one called the PowerPC. And that was a Big Endian machine. But those are long in the distant past. The Internet's about the only place out there when you send packets over the Internet and you want to send 32-bit words, they're actually sent in Big Endian order. And so at the network interface, you have to translate between those 2. So again, just to illustrate what I mean by this, is think of a byte value, 4-byte value like this. And remember that the way we write numbers is we put the most significant to the left and the least significant to the right. And so now with Big Endian is sort of the intuitive one from that perspective, in that the bytes, if you write the words in memory from the smallest address up to the highest, the Big Endian will sort of map to what you see. Whereas the Little Endian will look confusing, that you say 0, 1, 2, 3, 4, 5, 6, 7, because 6, 7 is actually the least significant byte here, and so that comes first in Little Endian order. And so it used to be people would get in passionate arguments about this. That's sort of in the distant past. And people saying, and the main feature in sort of argument of Big Endianness is this feature here, that when you look at it, it's easier to write down. But computers don't really care. They're happy either way, and so they just want one convention or another. And like I said, some hardwares can actually be by a sort of flag to flip it from being Big Endian to Little Endian. But the reality is most of the machines you'll encounter are Little Endian machines nowadays. But just to give you an example, here's some results that I got from actual machines. There used to be Sun machines around. So back in the old days, I could run this. I don't even know where to get a Big Endian machine anymore. So these are sort of legacy results. But you'll see that the main feature is between a Little Endian and a Big Endian machine, when you have an integer, the bytes get flipped around, so that the least significant byte comes first in a Little Endian machine and last in a Big Endian machine. And that's true with negative numbers as well, that you'll get the sign bits first in a Big Endian machine. Along, you'll see that the only difference between a 32-bit machine and a 64-bit machine is you have more zeros or more ones, depending on whether it's a positive or negative number. And again, a Sun, and if I had access to a 64-bit machine, Sun is now manufactured by a company called Oracle. So in principle, I could go get one of these machines and run this experiment, but it's really not a very interesting experiment, so I won't bother. So in principle, I could try it on a 64-bit Oracle machine and show you something different. So one thing that's kind of a useful tool, and the book goes through some examples of this, is a little program that will take a series of bytes, starting at some position start, and do it for however many bytes you request. And just print out, in hex format, the 2 hex digits that represent that byte value. And here, this term pointer, I'm using an unsigned char as a pointer type, a sort of generic pointer type. And so again, if I run this on a x86 machine, and I'm also, by the way, printing out the actual address that this character is stored at, too. And so you'll see that there's these addresses with a lot of 7Fs. What that means is it's in the upper end of this 47-bit address space. If you work it through, there's 7 is 3 ones, and then there's enough hex digits here to correspond to, so there's 11 hex digits beyond the 7. And you'll see that these addresses are at successive bytes, BC, BD, BE, BF, and the values are 6D, 3B, 0, 0, 0, 0. This is the least significant byte, and these are the successive bytes. And similarly, I can use this to examine pointers of various sorts, and I can examine different values and just get their low-level byte representations. And so I did this back when I could get to a Sun machine. It had one way of representing a pointer. And the main point is, even across machines, whether it's byte ordering or whatever, you'll get different values for pointers. There's no guarantee that when you load a program into one machine and run it, that it will use the same addresses as that same programming running on a different machine, even if actually they're identical hardware and operating system. There can be variation. Because pointers aren't, you can't directly copy a pointer from one machine to another. One thing about also is, regardless of byte ordering, the ordering of characters is the same. And so a string in C is always represented by a series of bytes where the final byte is 0, called null terminated. And the individual bytes correspond to the character codes for that number. And these character codes are just sometimes called ASCII format, which is a little bit old-fashioned, by the way. There's more modern character codes that can represent non-English alphabets. But the C standard is still back in the days of only supporting the ASCII format. Question?
When you're using the address of operator like yes, will that return an 8-byte number, and then you're passing it to a 4-byte number?
Yes. So this should have been. Well, no, this is good. So I'm casting. I want to show the 4-byte size of int, because this is an int I'm representing. The pointer, let's see, the code where it's printing the pointer, all this notation. %p is the directive to say print out a pointer, right? And %x is the directive to print out a hex representation. So it's printing out both the address, the starting position of that particular byte, and the value of that byte as 2 different things. Does that answer your question?
Print the pointer, the address of operator, return a number larger than 4 bytes.
Yes.
So when you pass it to 4 bytes, because pointer is an unsigned character, so that's 4 bytes.
But remember, show bytes is being given a pointer and a length. And so what this is, and what it's saying is, starting at that address, print out the next series of bytes for me, how many bytes I ask for. And in this case, I'm creating a pointer to this integer, but I want to show the bytes in that integer, the 4 bytes that make up that integer. And that's why I'm giving it the number 4 here instead of 8.
Yes, but what I'm saying is that since you're working on a 64-bit machine, couldn't that address be larger than 4 bytes?
Yes, it will be. And that's fine, because in this code, I'm using the %p directive to designate how to print out the pointer. And that will print it as many bytes as it takes for that particular machine that it's running on. So %p is actually a very handy directive if you have to print addresses, like for debugging purposes or something, because it will automatically adapt to whatever machine it's running on. Question?
Yeah, so what exactly is the pointer type? Is that like a void star or something?
Well, I've defined it to be an unsigned char here. So type def is a way to introduce a name for some data type, right? And so I've just declared a pointer, quote pointer, to refer to an unsigned char. If you did a void star, it would not be happy with this reference here, right? You can't reference. A void star is just a way to pass around a generic pointer, but you can't actually reference that element. So what I'm basically doing is saying, this reference is treat it like an array. Treat my series of bytes as an array and print out each of the bytes in that array. And so here where I'm, A is a number, and I'm taking the address of that integer and casting it to be an unsigned char star. So sort of a generic, slightly generic pointer, but not quite as generic as a void star. And then printing it out. These are good questions, by the way. OK, so the point being that strings are just strings, and that's the same from one machine to the next. OK, let's finish up today with some puzzles. And these have this annoying way of showing up on exams. So it's worth being able to do these kind of things. And you'll also notice I cleverly did not include the answers in the slides. So you can't just peek ahead and figure out what the answers are. So let's just go through them. But I actually worked them out to make sure I had the answers right. So if x, and basically these are sort of statements that you want to say these are either always true, and maybe there's some logic behind why it's always true, or it's possibly false, and you have to give some example that would make that false. So let's go through these, as many as we have time for, and see where we get to. So if I take x and I double it, multiply it by 2, if x were negative, am I guaranteed that 2x will be negative?
No.
No. So by the way, one general way to find counterexamples is to try t-min. It's a really good one. And that works here, right? If I take t-min, which is 1 and a bunch of zeros, I double it. It's like shifting it but left, and it will become what? 0, right? So again, assume that x is any negative number, and ux is its unsigned. Any two's complement number, and ux is what happens if I cast it to be unsigned. So is ux always greater than or equal to 0? Yeah. Mm-hmm. It's slightly more obscure. If I take
x is an integer, you say bitwise ampersand with 7. Is it always going to be equal to 7? Well, it depends on. Let's see. But 7 is all 3-bit set. Yeah, I would say that equals 7. And that's equivalent to x left shift 30 is less than 0. If that is the case, would it be less than 0? Yeah, that'd be true.
Off 7, you remember? Yeah. This is slightly more obscure. If I take x and I mask off 7, you remember, is the bit pattern 111. So if I mask off all but the lowest 3 bits.
Oh no, it could be 0. If x is 0, and you say that, then if you bit shift it left, it could be equal to 0. And if x is 3, then your sign bit, or 1. There's some values there, positive values, including 0, to where the right-hand side would not be true.
I'm already giving you the answer here. And then I shift it left by 30 positions. What can I say about the result? So I know that x must finish with 3 ones, right? And I shift that.
It doesn't have to finish with 3 ones. It's a mask. It only has 3 ones if it has 3 ones in x to begin with. Oh, so they're saying if that is true, then we shift, and then it is true, yeah. So if the left-hand side is true, then the right-hand side is true. If the left side is not true, then the right-hand side is not true.
And these will be the only 2 bits that are left after the shifting. And they will be in the most significant position. So what can I say about that number? It's negative. So this is a true statement. Rather obscure, but it is true. Is ux greater?
Ux, unsigned x, just some arbitrary value x. It's greater than -1? No. Because -1 in this comparison would get turned into an unsigned value, which would then be a very high value, which could be greater than ux. False.
It's almost true, right? The one counterexample would be what? 0. Well, actually, no, you're right. There's a lot of examples. It's hardly ever true. It's almost always false. I was wrong. The only thing that would make it true would be Actually, it's never true. OK, so it's never true.
Yeah, because -1 is all 1 bits, which would be the greatest value. Yeah, so it'd never be true because it's greater than not greater than or equal. X greater than y. If x is greater than y, then we can apply -x is less than -y. No. So say you have the situation where x is t-min plus 1 and y is t-min. When you negate those, x becomes a very high value and y is now still a very low value. It's t-min because negation of t-min is t-min. So that will be false.
If x is greater than y, is -x less than -y?
I mean, it's almost always true except for that edge
No.
case.
So by the way, one thing we didn't really cover is, what is the negative of t-min?
T-min.
And to see that, we can use our complement and increment trick. So when you complement and increment t-min, you get t-min. And that's why it's such a great counterexample. So in particular, if y is t-min and x is something else, then that left-hand part will be true, but the right-hand part will not be true. OK, x times x greater than or equal to 0. We've seen examples of that.
X times x greater than or equal to 0? No, because you can overflow. It drops to the left-hand side, and you can get negative values out.
False.
So x is greater than 0, okay, and y is greater than 0, okay, they're both greater than 0. Then x plus y is greater than 0, no, because they can wrap around.
If x is, this is kind of silly. If x is greater than 0 and y is greater than 0, is x plus y greater than 0? No.
X is greater than equal to 0, then negative x is less than or equal to 0. That is true.
Greater than or equal to 0 is -x less than or equal to 0. Gotcha. You're right. It's true, right? Because but let's take its counterpart. If x is
less than, there's a counterexample, which is
less than or equal to 0 is -x greater than or equal to 0. T-min, right? So, right. The point being that the largest, any positive number can be represented as negative, but there's one negative number that can't be represented as positive. And so that asymmetry is why you get different answers to these.
X bitwise OR with negative x, right shift over 31 is equal to -1. Let me try to work this through my head. So you have its negation plus 1. So let's take, if it was x ORed with its negation, it would be all 1s. But I think this one finds the bit position. I think this is like a little trick that I've seen before. Let me just get a buffer here. So say we have 0, 1, 0, 1, and then we negate that, which would be 1, 0, 1, 0, and then we add 1, 1 here. And then we OR them together, which would be 1, 1, 1, 1. So that's one example. If you XOR them together, then it would give you the bit position of the first bit. So if we did 0, 1, 0, 0 here, and we did 1, 0, 1, sorry, 0, 1, sorry, 1, 0, 1, 1, and then you add 1 to that, then it becomes 1, 0, 0. and then you XOR them together, you get 1, 0, 0, 0. Yeah, so this is the position of this would be 1, 1, 1, 0. So that 0 is like where the bit is being flipped. Sorry, the first bit position is here. If we shift it over right one, then we get the first bit position being the first bit in here and everything else zeros. But that's not what he was showing there. So let's take this example here with just OR. So you got 0, 1, 0, 0. We then negate that, which would be 1, 0, 1, 1 plus 1 would be 1, 1, 0, 0. And then we do the OR, which would be 1, 1, 0, 0. Let's do another one here. Maybe we do 1, 1, 1, 0. Negation would be 0, 0, 0, 1. Plus 1 would be 1, 0. Exclusive OR would be 1, 1, 1, 0. So that's taking a negative value, getting its positive inverse, ORing them together. Let's do 1, 1, 1, 1. Would be 0, 0, 0, 1. And then we would have 1, 1, 1, 1. So let's just put some decimal values here. Negative 1, negative 1, 1. This would be 6. This would be negative 8 plus 6 would be negative 2. And we order them together, we get negative 2. This would be what? 8 minus 6. No. 8, 4. I did this wrong. Sorry, my bad. I think this is 4, right? So we have 6, and I have 8. Wait, 4. 1, 2, 4. So that's 4. 8 minus 4, or negative 8 plus 4 would be negative 4, negative 4. This would be negative 8 plus 6, which would be negative 2. And then this would just be regular 2. And then this would be negative 2 as a result. So it seems like it's taking the absolute negative value of these things. Let's try the T min. That's always a good edge case, which would be 1, 0, 0, 0. Its negation would be 0, 1, 1, 1, and then you'd add 1, which would be 1, 0, 0. You then OR together, you get 1, 0, 0. So that would be negative 8, negative 8, and negative 8. So it's basically like converting this number to its inverse, making sure it's negative. It's like the negative absolute value. That's what this operation is doing. So it says take x's negative absolute value and then right shift it over 31. So just checking the sign bit. Is that equal to negative 1? Certainly not. Because if you right shift it over 31, there's 0 in the sign bit, and it can't be negative 1. It'll be equal to 1 if it was negative, and it would be equal to 0 if it was positive.
Can't be represented as positive. And so that asymmetry is why you get different answers to these. If I take x and I look at minus x and I shift them to the right by 31, am I going to get all 1s? This is a really weird statement. So it actually kind of works, right? If I take all 0s, and I subtract 1, I'll get minus 1. And I OR them? That works. So what's wrong with this? What's that? Oh, but if I shift this to the right 31 places, it's going to shift arithmetically. What's that?
Oh, interesting. I didn't take it into consideration that it's arithmetic shift because they're signed values. And then that will backfill out the ones and it'll equal -1. Yeah. There's no situation here where we don't have a 1. All positive values would become negative. Yep. That works. That's true.
Oh, I see. Oh, I'm sorry. I already jumped ahead to a different puzzle. X and minus x, and so you're right, actually. If the two numbers are 0, and I OR those, I get 0.
Yeah.
But you'll notice if it's anything non-zero, actually this will be true.
Yeah.
And that's an interesting feature. So there's a couple other puzzles, and I'll let you solve those on your own. We're all set for today.
Oh, that was interesting. So I was originally right, but for the wrong reason, because there's a single counter example, which is 0. So I think the test cases when you're doing these things, you really want to test T-min and T-max and 0. So the minimum, the maximum, and 0. And what's unsigned, the minimum is 0. I think those are the edge cases you really want to cover, and maybe like -1. There's a few things that you want to like test to just see what it does. All right, that was a good lecture. What time is it? It's past noon here. I'm gonna grab some lunch. Let me go ahead. I'll just kill that, and we'll pick back up on this website when I get back. Let me go to README. I'm gonna mark out this lecture here, and we'll come back over here. Oops. There we go. Cool. I will be back when I get done eating lunch and doing some cardio. So probably in an hour and a half, something like that.